Hello everybody, happy snow day. I wanted to record a couple of videos so that we don't get too far behind, and I wanted to cover some transitionary material that will help us get to talking about confidence intervals, our first statistical inference technique. The videos won't be very polished, of course, so if you do have any questions, please post stuff to Piazza, and I'll help as best as I can. So just to give a sense of where we're going, we're into the part of the course where we're going to start using the probability background we've been developing to understand what's going on in many of the very common statistical inference techniques. The first one we're going to consider is something called the confidence interval, which we should get to by the end of the week. So remember our general setting. We're going to assume that the data we collect is generated by a random variable. And typically speaking, we get to choose the random variable model we want to use, but we won't necessarily know what the best choice of a parameter is going to be for that model. So what statistical inference is going to do is it's going to take in our choice of random variable, this will be an assumption, and it's going to use the probability of the associated to the random variable to give us a sense of what the parameter is that models the data well, right? And of course, once we have that parameter, it's going to say something about the data that we've collected, say something about the population rather than the sample. Okay. Now, the other idea that we need to keep in our mind here is that typically speaking, we use sample statistics, which are special random variables, to estimate or approximate the parameters of the random variable model. Okay. So just as a quick example, remember if we assume that we're sampling from a normal distribution with a mean mu and a standard deviation of sigma, right? The two sample statistics that we were using as good estimators were our S-squared estimator and our X-bar estimator. Both are good in the sense that they're unbiased. In other words, the expected value of X-bar is equal to the mu we're trying to discover. And the expected value of S-squared is equal to actually the variance, not the standard deviation, but the variance of, again, the random variable model we're trying to discover here. And we also have good estimates for their mean squared error, both of which the more samples you include, the smaller the mean squared error gets. Okay, so where are we going with all this? We know the distribution of x, at least approximately, when we make certain assumptions, right? And so as an example here, if we assume that we sampled from a normal distribution, then x bar is going to have also a normal distribution. And the only thing that we have to update here is the standard deviation. We're going to divide out by the square root of our sample size. And then we also had the central limit theorem, which said something even more. If you assume that your sample size are very large, then it actually doesn't matter what type of probability distribution you're sampling from. X bar will still end up with a normal distribution. Its mean parameter is going to be the expected value of your underlying random variable. And its standard deviation is going to be, again, essentially the standard deviation over the square root of n for your underlying random variable. So this is a more general result, and we'll work with that. For a little while, we're just going to be assuming that we're sampling from a normal distribution. That'll be the case for more or less for today. So the name of the game becomes, how can we use these results to discover a particular parameter? In our case, that we want to discover the parameter mu. We want to know what is the mean of this normal random variable that we're working with. So what we're going to be doing over the next few days is we're going to be working through the following situations. Today we're going to work with the first bullet. We're going to assume that we know mu and sigma for that underlying normal distribution, and we're going to get some helpful results about x bar. None of these are new results, they're just going to be repackaged a little bit. After that, we're going to assume that we only know the standard deviation for that underlying normal distribution, and we're going to use some of the results from today to try to find, in quotes, mu using just x bar and that standard deviation. All right, so this technique here is going to be using a confidence interval, and we'll talk about that on Wednesday. And then finally, the most general form that we're going to talk about, hopefully by the end of this week, we're going to assume that we don't know mu or sigma for that underlying normal distribution, right? We're trying to discover that. We're going to try to find mu now using just x bar and our sample variance statistic. All right, so the last two bullets here are going to, again, use a technique called confidence intervals, and we should be able to go over many examples this week and possibly next week.